Hello, and I'd like to introduce the next session, which is our last presentation before the break this afternoon. So, um, this is Milad Musavi, who's a simulation services team lead at Maya HTT, and he's going to talk to us about maximizing offshore wind potential, empowering efficiency through digital twins and simulation. So, bringing a lot of this together. And please let me remind you again that we've got the Q&A function, so put your questions in as you're listening to the presentation. So over to you, Milad. Thank you very much.
Yep. Thank you, Deborah. Hi, everyone. This is Milad Musavi, and I'm Team Lead Simulation Services at Maya HTT. Before moving forward, let me introduce you to Maya HTT. At Maya HTT, we help organizations with their digital transformation journey. Siemens has recognized us as a top global partner in 2022. We're not just a consulting and system integrator, we also develop software with over 30 modules authored for Siemens used by millions worldwide. 75% of Mayans are scientists and engineers with hands-on experience in nearly every industry. Whether an organization is looking to better design, simulate, manufacture, or optimize operation, MyHTT combined engineering, software development, and AI expertise uniquely positions us to move you from concept to completion and beyond. So let's see what we're going to cover in this presentation. First, we're going to look at how we can enhance the design dependability and increase efficiency. We're just scratching the surfaces on these topics. How we can digitize the process of product development and certification, and we can reduce the maintenance costs and elevate overall performance. Before moving forward, first let's look at the business drivers for the global energy sector. Right now, the increased environmental concern, like environmental care, lowering NOx and other pollutants, and also guidelines that elaborated in the Paris Treaty on decreasing noise level are deciding what's the future, and also need for higher efficiency in order to maximize the output of the Earth's limited resources, keeping installations alive for a longer time and limit maintenance costs. And also peaks in the energy demand and intermittent power generation demands energy storage. So these are the trends that are happening, and you can see in the curve the aging part of the existing capacity and moving toward renewable energy. So let's look at the what are the latest trends in the wind energy landscape. There is a clear shift toward offshore wind parks. The logistics and the investments are heavier, but the availability of the constant wind speed is much greater than on land. And also there is a high pressure on the cost of wind farms, since at the latest auction, for example, the offshore wind farms are granted without any subsidy. So the return of investment must be guaranteed by low capex and opex. And lastly, the consolidation is taking place. The four biggest wind turbine makers, Vestas, Gamesa, Siemens, Goldwind, and GE, had in 2017 a market share of 54%, and the competition is increasing, and the aim is by advanced designs, but also but a clever fleet management, like optimized maintenance schedules or simply less maintenance, but by increased reliability of the installation to attract more businesses. So let's see how we can enhance our design dependability and increase the efficiency. One of the approaches is to go toward digital twin through digital transformation. You may have heard digital twins many times with very different or the same definition. So what exactly do we mean by digital transformation? It means digitally capturing all phases of your product development process, from the ideation phase with a product that helps you digitally define and improve your design and analyze its performance, to the realization phase with virtual production to digitize the manufacturing process of your product and anything used to produce it. And the last thing is to the utilization phase, where you digitally capture and relate all the elements of your product from design to actual product in use to ensure it performs as required throughout its life. So creating this holistic digital twin will help you in wind turbine development. How can it help you? It help you to increase the safety and reliability of your wind turbine, and also it addresses the speed and performance issues that you may have, and also it the more accurate simulations helps you to predict with a higher accuracy and precision what's the life of the product that you have, for example. And you can do all these steps in a cost effective manner because you're not producing the actual prototypes many times to do this development. And also you can benefit from these digital twins for your certification process, and you can address the on and offshore challenges that you might be facing. So let's look at the extent of simulation technology that can help us achieving these goals. In SimCenter portfolio from Siemens and also Maya expertise, we have a lot of softwares that can address fluid dynamics. We can address structural mechanics like composites, dynamics, static analysis. We can address acoustics, motions, electromagnetic, and many other things. But we don't stop here. We can combine many of these together, and for example do fluid solid interactions. We can do uh, aeroacoustics, or we can do vibroacoustics as an example. So we can combine these softwares. We have the expertise to combine these softwares to be able to uh, create a more holistic and more comprehensive digital twin of your system. Some of these models and examples are like here. We are doing the models of bed plate, actuators, or we can look at the load computation and use that as a base for certification. And we can model the gearbox, resonance detection, or crack propagation, for example, or also look at the offshore performance of our of the wind turbine, or structural strength and durability. So let's look at the what is included in wind energy performance engineering. So in wind energy performance engineering, you have to look at aerodynamic performance, you have to look at turbine engineering by itself, and you have to look at management and reliability and system performance. By looking at this, we can improve the efficiency, we can ensure we have a durable product, and also we can explore the blade and wind farm improvement. So let's go and look at improving aerodynamic efficiency. How can we do that? By creating accurate models in CFD, you can accurately model wind loads on blades and structures. You can increase the efficiency by design exploration and do a optimization study on your wind turbine by itself. Also, you can improve the energy production by design exploration on the entire wind farm. You can capture the ground effects and study effects of turbine placement, and you can easily go from one to include many turbines and see the effect of each of these on each other. We can go even further. We can utilize the mesh motion that we have in the softwares and our expertise to simulate forces on the wind turbine offshore. And we can include the forces from water and waves to be able to model accurately how the wind turbine platform is working all together. It's not just a blade, it's the entire system that should work together. We can do fluid solid interaction to ensure a stable operation, because we know under the loading these wind turbines can deflect and it affects their performance. We can simulate the steady behavior of the blades, different mode shapes to prevent accidents and ensure operation. And to increase the reliability, what you can do, you can go one step further. If you're installing these wind turbines in cold climate, you can do ice deposition on turbine blades and see how much you lose in terms of the power generation. But a wind turbine is an entire system and is designed as such. So more than ever, the global Siemens philosophy offers integrated and complete environment for balancing of multidiscipline aspects related to every level, from initial design to validation and then certification of the machine. So you can, if you have an integrated platform like what we have access to through Siemens and our expertise, uh, you can do acoustic behavior structural integration, durability and reliability, and system performance analysis. And you can go through a virtual prototyping process where you define the objectives, the requirements, then you go through this process multiple times. And after you finish your virtual prototyping, you can go into virtual and physical testing and combine that with a validation and certification process. And when you have a validated result, you can again go back to virtual prototyping and improve your entire system integrity by modeling a system level simulation. One of the example of this is, for example, here we have a model of a hydraulic lubrication subsystem, like all different subsystems of a wind turbine. We can do hydraulic lubrication, we can model the electronics, electrics, transmission, thermal control, and by applying the wind speed profiles, extreme condition scenario, or safety procedures, or realistic cycles, we can predict the energy and efficiency analysis. We can do thermal management and NVH analysis. So the base of this is an integrated framework that you can work with, which we can offer in through Siemens portfolio. The second process is digitizing of a process of product development and certification. So we did our digital twin for the, like, we created a product, a virtual product. Now what's the next step? So now let's talk about how product lifecycle management software, or PLM, can help you speed and streamline product introduction. Teamcenter is a digital thread backbone that connects your whole product lifecycle, connecting all the information and processes. First, you need to implement a data management system that connects your information from design through to manufacturing. This will enhance global collaboration across design domains and the whole business. With a data management system in place, your teams can better keep track of requirements. They can manage the data across the different bills of material and accurately track different configuration. PLM makes the connection with the entire value chain, from product development and manufacturing to developing to delivery, covering the complete product life cycle, including suppliers. So that's the Teamcenter that can do to make it more efficient to do the certification process, to go from ideation to manufacturing phase and beyond. But we can go one step beyond that. The other one is you can put a model-based system engineering on top of all this, which provide you with the integrated program planning and execution. So the evolution of PLM continues with additional information and teams concurrently connected to a digital twin. The integrated program planning and execution connects the program event gates with the schedules of execution. And in a product, for example, in a product definition phase, the systems engineering delivers a methodology to ensure you build the right product that meets the expectation of the target stakeholder. Going further, the connected engineering, the objective is to improve visibility across product development domains and utilize real-time collaboration with intuitive authoring and linking to quickly identify defects and also determine the impact and resolve issues in the most complex systems. And also it can go further. It can connect all this together with the product validation. So you get real-time data from product validation and you can see the affected parties or stakeholders in your design process, from the requirements to connected engineering. And you can see some of the product names that are beside each of these connected engineering in SimCenter portfolio. The last thing I would like to touch on is reducing maintenance costs and elevated overall performance. So far, using simulation and MBSC and Teamcenter, we came up with the holistic digital twin. So the next step is to benefit from these digital twins. Combining models and operational data is a core of a digital twin. So in this section, I'm going to give you an example of this usage. There are basically two approaches that you can do for reducing maintenance costs. You can have a digital twin that is data driven, or you can have a digital twin that is model driven. In this case, in the case of data driven, the specific details of a wind turbine are ignored or not known. Based upon the time histories of operational data only, one identifies trends which are representative of a potential damages. Artificial intelligence plays a key role in this one, and you can predict the next failures or etc. But this may not be valid in failure modes because nobody likes to have a wind turbine failed and cost them millions of dollars or billions of dollars to have a predictive model later. So the other approach is model driven. Here the core is turbine detailed information. This can be obtained from the models that were developed during the virtual prototyping phase, and they were validated with a limited amount of dedicated measurement in a turbine. Then the operation data is used to extract the equivalent cumulative loads for critical. If the design assumptions for these components are known, then you can do the aging analysis as well and calculate the remaining useful lifetime of these wind turbines. So let's look at one of the examples of this. In a real use case, if we use the SCADA monitoring data to look at 78 wind turbines on, let's say, 72 channels, wind speed, RPM, gearbox. This is just for the gearbox analysis, and we use the dual technique in here. We looked at the service history over 4 years, and this data uh, was stored inside the inside hub of Siemens platform. Then this data was used to train a neural network to be able to do a failure prediction and detection. On the other side, we used the digital twin model that was created and used this as SCADA load cases that was produced over time to look at the remaining lifetime of the gears and bearings for each of the wind turbine. So this is another example. We have many other examples that we used outlier detection or anomaly detections to be able to predict where the maintenance is needed or to prevent any catastrophic failures in the design because of a non-operational condition or the system working in a bad condition. So that's about. I just scratched the surface on all of these topics. Each of them have their own world. You can uh, dive a lot deeper in each of these, and I will be happy to answer any question that you may have on these topics. Thanks everyone for listening.
Okay, thank you very much indeed. Milad, thank you for the presentation. And so
My
the
pleasure.
floor is now open for questions. Please do put your questions into the Q&A. And we've got a couple of minutes before closing the session, so we've got time for a couple of questions. All right, so I think we'll kick off with the first question for you. Could you say a little bit more about how digital twins assist in reducing maintenance costs? And can you give an example of savings?
Yeah, of course. I'm going to give you one of the publicly available examples that we have at MyHTT that we used our expertise. So we developed a tool for anomaly detection and outlier detection, which uh, based on the information in the system of a boat that was done on a marine vessel. So based on the systems that were coming from the boat, this was trained, AI was trained with the combination of like a simulation data. It was trained, and then it could detect when the system was not operating in a right condition, and based on that was pointing the crew to the right place to fix those issues. So we did a pilot project with a customer. This was like 4 or 5 years of journey, and initially that this was a pilot, and now it is developed to a much bigger thing. But we did a first initial test with it, and the customer did not pay attention to those anomalies, and then they had a big blackout of the boat in the middle of a San Lawrence Seaway. So it cost them millions of dollars because of fines, because of maintenance, and being in the sea and not being able to operate. So from that point on, they saw the benefit of having this system online and being able to pretty much prevent any issue that comes in. And this system could see those anomalies 10 or 12 days before the blackout happened. So it can give them a significant, it could give them a significant amount of time to do this preventive maintenance before it happens.
Okay, thank you very much. Thank you.
Yeah, my pleasure.
Okay, and do you have any advice that you'd give to companies or organizations that are looking to adopt digital twin technology for their offshore wind initiatives?
So I would recommend there is one QR code on the screen if they can see it.
Mhm.
It's a scan for AI readiness assessment, so they can look at how ready they are in the process and then talk to experts in this field. We can help as Maya. We can help as well to look where they are in their process and how they can adapt to this and how long it may take, because it's not a 1 day process, it's a phase by phase and it takes time. But if it's done right, then you get a lot of benefit down the road with the and you need to have experts right beside you to be able to achieve this goal.
Yeah. Okay. Very, very true. All right. Okay. Well, thank you very much, Milad, and thank you for your presentation.
Yeah,
I
my
think we'll
pleasure.
thank you. I think we'll draw the session to a close now because we want to have a short break before going into the panel discussion. Um,
Yeah,
so thank you again for your presentation. Um,
yeah,
the the networking break now will run until 3:30, so we'll reconvene at 3:30. And please do use the networking function, the instant messaging, and the My Meetings function within the software to connect up with the presenters that you've heard from today and others that you want to talk to. And then I'd just like to invite everyone to join me at 3:30, 15 conference room 2, where we'll be having the panel discussion, bringing a lot of these things together that we've heard about today across 4.4 for offshore energy technology. And we'll be looking at continued steps in implementing smart solutions into the asset's complete life cycle. So thank you very much. Enjoy a short break and see you again at 3:30. Thank you,
yeah.
Milad. Bye bye.
Thanks everyone. Have a good day.